Hello everybody. Once again I am here with you for the another session of the logic gates, and already we have seen basic gates, how the NOR gate and the NAND gate is to be as an universal building block, and the basic parts related with the number system already we have seen. Now today we will see additional gates, that is ExOR gate or the ExNOR gate, that means exclusive OR gate and exclusive NOR gate. How they are differ from the our regular OR gate and the NOR gate, that is also we will see in this lecture. So let's start with this, what exactly this exclusive OR gate is to be there. So as far as the OR gate is going to be concerned, we know that the logic behind the OR gate is to be simply any of the input is high, output is going to be high. But here in this exclusive OR gate, a little bit difference as far as this OR gate, regular OR gate and the exclusive OR gate is to be there. Why this name exclusive OR gate given to this? It is also giving you the high output for the any of the input is high, but the condition is to be when the both the inputs are high, here it is to be 0. In other case, any of the input is going to be high, then and then only this is giving you high output. Or in simple way, exclusive OR gate is also to be when all the inputs are same, that means 0 0 it is giving 0, and 1 1 it is also to be 0. That means when all the inputs are same, the output will be 0. It is what the case, but what exactly the correlationship in between this OR and exclusive OR gate is to be there. Simply if you look at this addition part, for this two inputs are to be there, 0 0 addition will be definitely 0 is to be there. For the 0 0, 0 is the addition. 0 1 addition will be 1. For the 1 0, 1 plus 0 it is always 1, and 1 plus 1 you will say the addition is 1 0 in binary, but here sum is 0, carry is 1. So here if you look at this case where the outputs are going to be concerned, here only the sums are taken into account, not as in carry is to be concerned. So this is what the basic difference as far as exclusive OR gate and OR gate is to be concerned. At the last part, this is 1 1 condition is to be there. Here in this OR gate, there will be the output to be taken as a high, but here only the sum is taken into account, not as an carry is to be there, and that's why the output is going to be as an here to be 0. So this is what the basic difference between the OR gate and the exclusive OR gate is to be there. And due to this, the logic is become as an when all the inputs are going to be same, output is to be 0. That means for the 0 0 output is 0, for the 1 1 output is also to be 0 is to be there. So this is what the condition and the truth table for the exclusive OR gate is to be there. And then let's see how it is going to be implemented or how it is going to be notified. In simple way, if I want to represent it, it will be given as a y is equal to a complement b, or a b complement is to be there. That means any of the input is going to be high, it is going giving you as an output is to be high. Means either one is a is to be 0 at that, and the b is to be 1, then it is giving you high output. Or either a is going to be high or b is going to be 0, at that stage the output is to be 1. And that's why here the whatever be the condition we have taken, the output is written in this form, that is y is equal to a complement b, or the a b complement plus b a b complement. That means any of the condition if you are putting, it will give you high output for only that particularly 0 1 or 1 0 condition is to be there. And that according to that, whatever the values you will put, the result will be likewise there. So this is what the exclusive OR gate is to be there, and how it is going to be implemented. If you look at this diagram, it simply shows how it works, as an it is this exclusive OR gate is made with using the three gates are to be there, that is one NAND gate, one AND gate, and one OR gate is to be there. If you look at this is what the NAND gate is to be there, because bubble is in front of this AND gate symbol, and that's why this is the symbol for the NAND gate. This one is your OR gate, and this one is to be your AND gate is to be there. So using these three gates, the exclusive OR gate is made, and the symbolical representation is shown in this C diagram, where the symbolical representation for the exclusive OR gate is likewise this. So how either it is giving us a correct output according to the whatever the truth table we have seen. So let's have a look at this 0 0 condition is to be there. Sorry, here if suppose the 0 0 condition is taken into account, At this stage, if you look at this circuitry that is in front of you, it is now this is okay. So see, this is for the first condition, that is 0 0 according to the truth table. And again, when the two inputs are there, number of probabilities of the inputs are going to be 4: 0 0, 0 1, 1 0, and 1 1 is to be there. So the first condition is 0 0. Now look at this B is also connected to the one point of the input of this NAND gate. That means this first NAND gate is getting the input to be as in 0 0. And as far as according to the our NAND gate truth table, when what is exactly the logic for the NAND gate? That logic is to be completely opposite to the AND gate. What is the logic for the AND gate? That all the inputs are high, output is going to be high. That means reverse to this NAND gate will be when the all the inputs are high, then only output is 0. And here the 0 0, definitely the NAND gate will give us to be as an output to be as a 1 is to be there. As far as the OR gate is going to be concerned, it is to be what the condition is to be there, it is simply as an 0 is already B is to be there, but here it is A is also connected to the input of this OR gate. Second gate is to be your OR gate is to be there. And definitely we have the input for this OR gate is to be 0 0. And what is the logic for the OR gate? When the any of the input is high, output is going to be high. And here both the inputs are 0 excuse me, that output is also going to be 0 is to be there. And this output of the first NAND gate and the second OR gate is given to the third gate, and that means output of this NAND gate and the output of this OR gate is input of the AND gate, that is the third gate is to be there. And for the AND gate, input is 1 0, but again AND gate is such a gate which have the logic when all the inputs are high, then and then only output is going to be high, otherwise it is 0. That means the output you will get as an 0 is to be there. So first case where the A B is to be 0 0 condition is to be there, we are getting the output to be as a 0 is to be there. So if you look at this case, the truth table is to be there, which is going to be similarly matching with this truth table. That is what the 0 0 is the case where 0 0 the output is going to be 0. Now look at the another case, that is the another one 0 1 is to be there. That means A will be 0 and the B will be 1. In that case, what will happen? So let's see what exactly this either the circuitry giving us the similar output what the truth table is to be showing. So look at this diagram neatly, that again we are looking for the condition that is to be 0 1 is to be there. That means A is to be 0, B is going to be 1. Now here for the first NAND gate, which is in this diagram, we have the input as an 0 and that is it is 0, and 1 is from the B, that is 1. That means for the NAND gate input is 0 1. And again we know that for the NAND gate we know the logic, when all the inputs are high, output is 0, otherwise it is high, means 0 1 will give you output to be as an 1. And secondly, for the OR gate, we have the input 1 from this B and the 0 from this A. And OR gate, we know the logic that any of the input is high, output is going to be high is to be there. That means for the 0 1, this second OR gate will give us output to be as an 1. This output from the NAND gate and this output from the OR gate will be input for the third AND gate is to be there. And that means for the AND gate input is 1 1. Already we know when the output when the both the inputs are high, output is going to be high for the AND gate is to be there. That means for the 0 1 condition we are getting the output to be as an 1. Let's see either this is going to be matching with our truth table, and if you see, this is definitely matching with our truth table. That is, if you see this 0 1 condition is to be there, it is giving us 1 as an output. Again for the 1 0, this is going to be vice versa only, and you will get the output to be as an 1 also. Again we will see in detail, we will not let it go. We will see how it is going to be happening. So let's see again this for another condition, that is 1 0 is to be there. That means A is to be having here 1 and B is having to be 0. Now this is our NAND gate again. We have the input here to be as an 1 from this A and the 0 from this B. And as we know, for the NAND gate, when the input is 1 0, the output is going to be what? It is definitely, again I will repeat, the NAND gates logic is to be there. When all the inputs are high, output is going to be 0. Definitely we are getting output to be as a 1 is to be there. So this is what the condition output we are getting for our first NAND gate is to be there. And here the case where the second OR gate is to be there, this is we have the input that is 1 0 is to be there. That means again for the OR gate we have the input 1 0, and as we know that 1 0 input that OR gate will give, again according to the logic, any of the input is high, output is going to be high is to be there. That means we are getting output as an 1 is to be there, high is to be there. Again for the AND gate we have the input 1 1. As we know, when all the inputs are high, output is going to be high, and that's why for the 1 0 condition we are getting the output to be as an 1 is to be there, and this circuitry giving us likewise. So if you look at the condition, if you seen through the truth table, again for the 1 0 condition we have seen here, for the 1 0 condition output is high is to be there. Now let's see what happens for the input when it is going to be 1 1. So let's check it out for the last part, and that is to be as an 1 1 is to be there. So here it is to be there. Sorry. This is what the 1 1 input is to be there. Definitely this NAND gate is having the output input to be as an 1 1, and as we know, when all the inputs are high for the NAND gate, the output is going to be 0 is to be there. Similarly here again for the OR gate, the inputs are nothing but to be A is 1 and B is also going to be 1. That means 1 1. For the OR gate we know any of the input is high, output is going to be high. Definitely output will be 1. But for the AND gate, this third gate, we have the input that is 0 and 1, and we know when all the inputs are high, then and then only output is high for the AND gate, and definitely for the 0 1 input the output is 0. That means for the 1 1 input we have the output to be as an 0, which will satisfy, this will satisfy our fourth condition is as shown in the truth table. And in this way this circuitry works as an exclusive OR gate is to be there, and that's why the logic for the exclusive OR gate is to be there. When all the inputs are same, output is 0. That is what to be the case. So let's look at opposite to this. There is a exclusive NOR gate, same thing is to be there, only the exclusive NOR gate is to be there. That means what is the exactly logic I already told you in this case. For the exclusive OR gate, that is any when all the inputs are same, the output is going to be 0. For the exclusive OR gate, 0 0 output is 0, 1 1 output is 0. It is two input gate, that's why. And as reverse to this exclusive OR gate will be definitely when all the inputs will be same, output will be definitely 1. That is exclusive NOR gate. Let's see either it is going to be there, is it in same way. So moving forward for the exclusive NOR gate, this is what the symbol for the exclusive OR gate, and here is the exclusive NOR gate is to be there. See what I told you, that is to be here in this truth table, that it is showing you clearly that for the 0 0 the output is 1, for the 1 1 output is 1. That means when all the inputs are same, output is high, which is logic exactly opposite to our exclusive OR gate is to be there. For the 0 1 condition it is 0, for the 1 0 condition it is 0. So let's have a look at how it is going to be matching with the either circuitry is to be there. So to look at this circuitry, and it is again to be given some sort of SOP and pause form, That we will see in detail when we are looking for the SOP form or the POS, that is the sum of the product or the product of the sum is to be there. According to that, this basically Boolean expressions for these gates are to be there, and Y output is according to that A complement, B complement, or AB is to be there for the SOP, and Y is the nothing but to be A or B complement, and A complement or B is to be there. Here the operators are taken to be OR as an OR operation as an plus, and AND operation as an dot is to be there. So if you look at this, is as far as the sum of the product SOP is to be there, it is A complement, Y output is A complement and B complement, or means addition, A or A and B is to be there. And for the POS, that is product of the sum, that means here the product is going on for the sum, and here is sum is to be going on for the product, and that is why it is to be SOP and the POS is to be there. And for the POS, that is product of the sum, it is written as a Y is equal to output for this gate is to be A or means plus, B complement, and means dot here, and A complement or B. So this is what the case where it is to be written in this as far as the exclusive NOR gate is to be there. So looking at this case where the our exclusive OR gate circuit, logic circuit, electrical logic circuit is given in this form is to be there. So this is what the logic circuit where it is going to be used, and in this case the two AND gate, two NOT gate, and one OR gate is going to be used. Here if you look at this case, here one, here is this 2, and here this the third is OR gate is to be there, and these are the two NOT gates are going to be used. So if we have to look at this case where to be as an exclusive NOR gate is to be there, so putting the one condition that is to be as an 0 0 is to be there. If you look at this case, the definitely 0 0 input will be for this AND gate, and as we know 0 0 output is 0, and definitely this output will be go to the third gate, that is 0 for the one case to the third OR gate is to be there. And what exactly this is for the your AND gate is to be there, second AND gate, we have here this 0 is coming from this, but there is a NOT gate in between this AND gate and the B is to be there. This 0 will convert into 1, and again this 0 from A is also coming through this NOT gate, and that's why the 0 will become to be as an 1. So definitely at the input for the second AND gate there will be 1 1, and as we know for the 1 1 input the AND gate is also giving us to be as an 1 is to be there. So in this case, if you look at for the OR gate, any of the input is high, output is going to be high. That means 0 1, definitely it will give us output to be high is to be there. That means for the 0 0 condition, we have the output is going to be 1 is to be there. And if you look at this truth table, we have the same results as far as this truth table is to be there. Look at this case, the 0 0 is to be there. It is giving us output to be as an 1 is to be there. Similarly, let's see now the 0 1 condition is to be there. What happens for that case? So looking for the another case, that is 0 1 is to be there. So in this case, when we are putting 0 for this case as an A is to be 0 and B is going to be 1. So in this case the 0 will be here for the AND gate, and for the first AND gate input is 0 1, and as 0 1 input is to be there, output will be 0, because AND gate is having the logic when all the inputs are high, output is going to be high, otherwise it is 0. That means for the first gate the output is 0. But if you look at this case where it is to be as an second AND gate is to be there, this is what the case where it is to be as an particularly, if you look at this case, the 0 is coming from this A, but here it is first NOT gate is to be there, that will give us as an output for this is to be as an 1, and 1 will be input for the second AND gate. For this B, 1 is to be there, and the complement of this NAND gate is again here it is another NAND gate is to be there, and that's NOT gate is to be there, and that's will 1 will convert into 0. That means for this AND gate the input is 1 0, and for a AND gate, when the 1 0 is the input, output will be definitely 0. And for this third OR gate, the input is 0 0, and definitely output will be 0 is to be there. That means for the 0 1, the output is becoming to be as an 0 is to be there. So this is what the case. If you look at this 0 1 condition is to be, sorry, 0 1 condition is giving us output to be as an 0. Same thing will happen for this 1 0 condition, only vice versa changes are to be there, and the output will be 0 also. And let's see what happens for this 1 1 condition. In this case, either we will get high output or not. So let's see for what happens for this last case as an 1 1. And look at this circuit diagram when we have the input is to be as an 1 1. So definitely input for the first AND gate will be 1 1, and as we know, when the 1 1 input is to be there, output will be 1 for the AND gate, because all the inputs are high, output is going to be high. So output will be 1, and again this 1 is going through this NOT gate, and that will become inverse complement, that is 0. So 0 input will be for the second AND gate is to be there. Again same thing will happen, B is having 1, but here is NOT gate, that will convert this 1 into 0, and again this 0 will be input for the second gate. Means that's why the second AND gate is having the input 0 0, the output will be 0. And for this OR gate, it is the condition where the 1 0 is the input, that means, sorry, 1 0 is the input, that will give us output to be as an 1, because any of the input is high, output is going to be high. If you look at this case for the truth table, this circuit diagram is giving us the same output for this case, that is for the 1 1, the output is also going to be 1 is to be there. So this is what the case where the exclusive NOR gate is the such gate having the logic when all the inputs are same, the output is 1 is to be there. And for the exclusive OR gate, the condition is, or the logic is, when all the inputs are same, output is 0 is to be there. And for the exclusive NOR gate, it is completely inverse of that, and that is to be condition here as shown in this truth table, that when all the inputs are same, output is high is to be there. So this is what the complete part of this exclusive OR gate and the exclusive NOR gate. As far as symbolical representation, I have already told you that it is nothing but to be y is equal to given with a and b, or a complement, b complement is to be there. So again, thank you for joining this session, and be at home and be safe. Thank you.